Right, so previously we have looked at how to use the Green's function in order to solve the simple harmonic motion with the applied force. So in this video, we are going to look at how to do that using Green's function, but for the case when you have friction, right? So it is no longer a simple harmonic motion, but then you have damping. And in this example, we are just going to consider an underdamped motion. And if you want to kind of refresh what is under dam, what is critical dam, and what is over dam, you could look at my previous lectures, right? So now let's go to this Green's function, right? So in the previous video, we looked at the simple harmonic motion with constant force, and we have derived the motion for the object attached to the spring in this case, where you have y equals to this equation. So just this c is sometimes written as omega. So this c is written as it's actually a function is depending on the k and m of the system, right? So now if you have to consider friction, remember in the previous lecture we talked about writing the same expression, except that we do not have this one. We do not have this exponential minus t minus t prime term, because in that case we are considered simple harmonic motion. But in this case we have a damping, and since you have under damp, you have all oscillation, but it's going to decrease over time. Then you have to add in this expression over here. And 10 in this case, this is the force that is acted upon the system at the initial time t equals to 0. So here you have 10. So this is going to be a constant, and you can remove it from the integral. So you take it out, and now you see you have to integrate a more complicated expression, slightly complicated. You have exponential term over here, which depends on t prime, and you have a sine c t minus t prime, and this is an integration with respect to t prime from 0 to t. So the limit for the integration is sometimes we have to be very careful here, okay? Because here we start with t, but in the actual expression they write this as negative infinity. It means up to a point where the motion that you are going to consider. So if your force is acted upon at time t equals to 0, so you have 0 here up to time t. Okay, so if you consider to apply the force at certain time, let's say t equals to 5, then you will have 5 up to t. Okay, right. So now you have to integrate this. So I will leave this derivation steps as your exercise. You will recall how to do this in a lecture which I will do with you over the online class later on. So here this is slightly tedious for me to show on the whiteboard, but you can do this. And now once you have finished deriving, you will have an expression like this. Okay, so I have not inserted the limit of the integration over here yet, but this is the expression that I will get plus this one here. And now what I just need to do is to put in t prime equals to 0 and t prime equals to t into this equation, and finally I will have this this expression, this function for the motion of the object. Okay, so right, so that is how we use the Green's function in the simple harmonic motion that we discussed earlier, and in this case when we consider friction. Okay, so again, you see there is no you do not have to consider initial conditions in order to determine coefficients a and b like what we have done before. Right. So in the next few minutes, I will just show the plots on the octave, and that will be the kind of like a sum up what we will touch on the Green's function. So here we are going to plot the function that we obtained from the Green's function method. Here, in order to do the plot, we still have to define the t, which is the time, the k, the spring constant, the L, and the m, and then we need to calculate in this case the beta, which is the square root of c squared minus b squared.
Right. So as we have done earlier, we have actually shown that this is under damped motion, right? So we will skip that, and now we will just plot our y, which is, I call this as a y green to say that this is the green function, and underscore friction to say that this we consider friction in this case. So this is I've actually typed the equation ready for you, else it will take too long a time to do all this. So now I will just enter, and we have all the value for y as a function of t. Now let me just plot this. So now I will plot the y as a function of t, and I put the symbol star here, and now this is the resulting plot that you have. The x-axis again is the time, and y is the y that we have obtained just now. And then we see, starting at the time t equals to 0, you start from the place where the object is actually depressed downwards because you apply the force, right? So when you apply the force, and then after that when you let it go, so it's going to go up, it's going to oscillate, except that it will now the oscillation is going to be decreased in magnitude over time, and then you have over dam, the same kind of picture that you got earlier on, except that this is using Green's function. So this whole exercise is basically kind of like to introduce you to how you actually use Green function in order to solve this second order differential equation, right, for the harmonic oscillation. Right, so basically that's it for the Green's function. So I hope you have enjoyed this video. Thank you.